So, good evening, everyone. Welcome to today's live interactive session. Um, in the previous class, we had study problems where we solved uh, problems regarding this reinforcement. Okay, reinforcement of the foundation soil. Okay, foundation soil for an embankment using geosynthetics. All right. So initially we just had gone through the theory. We went through the theory, and then actually uh, we had gone through the solve one numerical. After that, as we had time remaining, we had seen the concept behind unpaved roads and how, excuse me, and how geosynthetics can actually be used to reduce the thickness of aggregates in unpaved roads. So there we are seeing that if we use a layer of geotextile or geogrid, we can reduce the we can reduce the uh, thickness, okay, of the aggregate layer by a we can reduce the thickness of the aggregate layer by a large extent, isn't it? Right. So we had done that, and in today's class also. So as I had seen that not much topic, like not a vast topic was covered, just a small topic regarding this use of reinforcement or ties to improve the bearing capacity studied. So that is not a big topic. So that topic was just discussed in two lectures. So today we will try to uh, try to recap whatever was taught in the theory class, right? So, uh, so, so today we will be trying to uh, recap whatever was taught in the previous session. That is, what was actually taught in the theory class. That is the use of reinforcement. Okay, the use of geotextile or tie or any other steel strip, any reinforcement to improve the bearing capacity of the soil, how that is done, the theory behind it, and then we will be solving the problem that was discussed in the class. Okay, and then we will see if we decide to use say a different width of strip footing, then how does everything change? Okay, so we'll be doing that. So uh, as only this topic was covered, right? Only this very topic of this increasing bearing capacity for foundations using reinforcement. Only this topic was covered. It is not a very big topic, so this was just done in two lectures. So I will also be just reiterating that part today, and then we will be trying to solve the problem. All right. So you will see how much time it takes, and if there is some more time remaining, then we will see what. All right. So let us start. Okay. So as you know, the first question is what is shallow foundation, right? So when do you call a foundation a shallow foundation? So if the depth to the width ratio is less than or equal to 1, then it is generally called the foundation is generally called a shallow foundation, right? And if the depth to width is greater than actually more than 1, then it is a deep foundation, right? So what are the shallow foundations? Shallow foundations are generally rafts, okay, rafts or wall foundations, that is the steep foundation. These are generally shallow foundations. And what are deep foundation? Deep foundations are those for which the depth to width ratio is greater than 1. Okay, the depth is larger than the width, much larger than the width. So, for example, the most common type of our deep foundation is piles. Piles are the most common type of deep foundations. Piles, then caissons. Okay, those things are our deep foundation, right? So, in case of shallow foundations, how do we actually uh, calculate the footing area? Okay, the area that we need to provide so that the oncoming load is safely transferred to the soil. Okay, is here footing area is equal to load still transferred to the soil divided by the allowable bearing pressure, right? So when I say that the loads are safely transferred to the soil, that is ensured by this allowable bearing pressure, isn't it? So this allowable bearing pressure actually ensures that our settlements will be within range, and also the load that will be coming in onto the soil would be more than the strength of the soil, that is the more than the inherent resisting the capacity of the soil. This the soil would be able to take that load without undergoing shear failure. Right. So two criteria which satisfy this allowable bearing pressure. One is the settlement criteria. So we cannot have unlimited settlement. So allowable settlement, from that we get one pressure, and other pressure we get from the shear strength. It is the maximum load that ultimate load that it can take without undergoing shear failure. Without the soil undergoing shear failure. So the minimum of these two pressures actually give us the allowable bearing pressure. Sorry. Now, as I said, the pressure transferred to the soil should not exceed the safe bearing capacity of the foundation soil. Right? So the safe bearing capacity, this safe bearing capacity actually depends on the soil strength parameters mainly. That is the cohesion, friction angle, and other than that, other than the strength parameters, it depends on the depth effect, the shape effect, all these things. So if we can recall IS 6403, we have seen there that its depth effects and shape effects, all these things were considered using the depth factors and shape factors. Alright. Next, we have the settlements of the structure under the imposed pressure should be with safety. That is the same bearing pressure. So again, so the settlements or the differential settlements, okay, the differential settlements those should be under limits, and these differential settlements, the limits of these differential settlements actually vary from structure to structure. So for RCC structure, for masonry, for steel structure, these are different. Alright, and these are clearly mentioned in the code. Okay, in the Indian standard codes, these are properly given. The level bearing pressure is obtained at the minimum of the safe bearing capacity and the safe bearing pressure. Right. Now, this thing already we had discussed previously also. So just again, we will just recap this. So the general shear failure in general, generally there are three modes of failure. Right, the general shear failure, local shear failure, and punching shear failure. So in general shear failure, what happens? There are clear shear, this failure of the soil, and there is good ground heaving. It is seen. All right. And if you plot the load versus settlement curve, you will get something like this. So that is the general shear failure. The general shear failure generally occurs for dense sand or overconsolidated clays. So for granular soils, for 5 greater than, generally for 5 greater than 36 degree, we have general shear failure. Then we have the local shear failure. In the local shear failure, this see this sorry, these failure surfaces here are not that properly formed. Okay, is unable, is not completely formed, but still we have some ground heaving. The local shear failure for loose sand and for normal enough. And then we have the punching shear failure. This happens for extremely soft soil. So there no failure surveys therefore. That is the foundation just settles, goes, punches into the soil. Alright, so these are the three modes of failure. So why do you use the shallow foundation? Shallow foundation generally result in good cost economy compared to deep foundation. Okay, deep foundation alternatives in clay. Alright, so here we can see three images where in the first uh, image we can see this footing of width V and a number of geogrid layers are provided to reinforce the soil. So this will actually increase the bearing capacity of the soil. And in the second image you can see geotextile layers are provided, and in the third image you can actually see reinforcement ties are provided. Okay, reinforcement is a steel strips. Okay, here said steel strips are provided. Okay, to increase or the increment the bearing capacity. Now, actually, what happens is if we see this graph, we can see that due to the reinforcement, right? So, if we put reinforcement in the soil, the stiffness of the soil is actually increased. So, this dotted line is actually for unreinforced soil, right? And all the these graphs, all the other plots, these are for reinforced. So, the here n equal to 1, n equal to 2, 3, 4, 5. This means the number of layers of reinforcement that you have provided. All right, this n numbers is wise for the number of reinforcement. So you can see that as we increase the number of reinforcement, the load capacity is increasing, and also the soil is actually becoming more stiffer. Okay, so here initially if we take the initial modulus, it was something like this, but then you can see it has become more stiffer. Okay, right. And one more thing, if you see here, you can see that large settlements are actually required to mobilize the high bearing capacity. So in the reinforced case, you can see that if you want to mobilize this high bearing capacity, large amount of settlements are actually required to mobilize this. Now apart from geotextiles, geogrids, steel strips, geocells are also used. Okay, geocells are also used to increase the bearing capacity. Right? So here you can see a footing of width B. Okay, underneath that at depth U, a geocell of height H, geocell matrix of height 8, width B, and this aperture with D has been provided. Right, has been provided, and you can see the mode of failure in this image here. So the load is transferred at an angle alpha to the geocell layer, and the failure surface actually develops at the bottom like this. Okay, the failure actually, this is similar to what we had how we had solved the problem for the embankment. So we had an embankment, right, with an embankment of huge width. Here we had soft slate, the clay layer in the between, and in the bottom we had stiff soil. And what we did was we still provided a geocell here to increase the strength of the. Okay. So these are the improvement with different geocell matrices of different B by B. There is different width to width ratios. So here again you can see that the stiffness is increasing as you provide geocell, and this is for the reinforced case. Stiffness of the soil increases, and also the low bearing pressure is increasing by a huge amount. But again, one more thing we have to consider here is that a large amount of settlement is actually needed to mobilize this increasing bearing pressure. Now here various researchers had actually provided given the optimum parameters. Okay, optimum, which is U by B's ratio, is nothing but the optimum depth of the first layer that should be provided. Okay, Is U by B, then this del H by B. Del H by B means the spacing, optimum spacing, right? This B by B means the width to width ratio, and is the number of layers. So here you can see that many researchers had done many experiments by taking many different types of reinforcement, and they had actually suggested some optimum geometric parameters so that we can get maximum benefit out of them. All right. Then we have this improvement factor and settlement ratio. Okay, so what is improvement factor? Improvement factor is nothing but the pressure on reinforced soil divided by the pressure on unreinforced soil. So obviously, it is called as improvement factor. Why is it called improvement factor? It is called improvement factor because obviously when we reinforce the soil, the pressure that we will be getting, it will be higher than that of the unreinforced soil. So this improvement factor should be greater than, obviously should be greater than 1. Now what is the settlement ratio? Settlement ratio is a dimensionless quantity again, where it is a ratio of the settlement to the width. So here we can see that there are many graphs where the result is uh, actually presented in terms of the improvement factor and the footing settlement, right? So here you see that with the use of reinforcement, this improvement factor is increasing by large amount, right? Again, you can see this is for geogrids. Okay, this is for geocell. You can see the star line is for geocell. With the use of geocell, the improvement factor is increasing by large amount with increasing settlement, right? And again, this is on more for this geocell and these different arrangements of geocell. Okay, and here we have this the improvement with geocell, and also when this type when the soil is changed. Okay, this when the soil, that is the relative densities are changed of the relative density of the filling soil, the soil within the geocell is changed. So for that we get different effects. So what are the most important points should be kept that we should designer should keep in mind while designing the reinforcement for a foundation? Okay, these ones. The depth of the first layer of reinforcement. Okay, the first layer of reinforcement that you are providing beneath the foundation, that depth is very important. Okay, the depth is crucial. The total number of layers of reinforcement, so it is up to the designer to optimize the number of layers so that we can get optimum increment in bearing capacity. All right. Then we have the length of the reinforcement, the optimum length of the reinforcement that we should provide, the vertical and horizontal spacing between the layers, the type and the material of the reinforcement, whether we are to choose geotextile or geocell or geogrid type, and what material of say geogrid we need to choose. That is up to the designer to choose. Also the shape and size. Now Now, in our case, where we are to reinforce the soil, okay, reinforce the soil, and where we are to increase the bearing capacity of a foundation, these three modes of failure can happen: mode 1, mode 2, and mode 3. Okay, these three modes of failure might happen. In this case, what happens is that, say, we have a large number of this reinforcements placed at a depth. Okay, the first reinforcement du is placed in depth greater than you 2/3 of the width. Okay, 2/3 of this width. Then what happens? This acts as if we have a soft soil layer between the sandwich between this foundation and the stiff soil layer. similar to what we had done for this geocell. In this case, the failure will happen that that way. Okay, what we had discussed in the previous class. How the failure occurred in the case of that geocell reinforcement that we used underneath the embankments. Okay, there also we had soft soil sandwiched between layers. So here the failure also will be uh, occurring that. Okay, so in that mode, that case, what happens? The bearing capacity failure of the soil above the reinforcement actually occurs. Alright. The next case is when u by b is less than 2 by 3 and we are using less number of reinforcement. Okay, less number of reinforcement or shorter reinforcements. In that case, what happens? There is chance of pull out failure. Okay, there is chance of pull out failure. It means the load coming onto the soil, a load coming to the reinforcement is higher, and there are chances that this reinforcement will get pulled out. Okay, these ties will actually get pulled out with the soil. Okay, this will actually get pulled out with the soil. And in the third mode of failure is that when there are large number of ties and long ties. At that case, what happens is there is tensile failure. That means the reinforcement tend to break. Okay, the reinforcement tend to break and one by one. Say first set will break first, and the second layer will break first, and like this, gradually it will keep on breaking, and this failure will keep on propagating. Okay, so these are the three possible modes of failure in which this reinforcement, in which this foundation might fail even when we have provided reinforcement. Okay. So some general guidelines are generally given to consider the number of layers, the depth, the width, and the uh, depth of the first layer of reinforcement. So these are here, these are given here. The depth of the first layer of reinforcement du is generally in the range of 0.25 b to 0.5. Okay, it's generally in the range of 0.25 b to 0.5. Okay, okay. The number of layers of reinforcement is generally kept between 3 to 6, and the length of the reinforcement layer is ideally 7b, but more than 7b is generally not economic. Okay, it's ideally about 7 times of the width. Generally, uniform vertical spacing varies from 0.1b to 0.4. Okay, depending on the number of layers. Okay, so if we are providing lesser number of layers, then what we can actually increase the spacing a bit. Okay, so that we get our desired factor of safety. So we will see that later how to do that. Then also must ensure that the reinforcement should have sufficient tensile strength. Obviously, we should ensure that the reinforcement has sufficient tensile strength. Now we come into the theoretical analysis of reinforced foundation as far as Pinkett and Lee. So Pinkett and Lee, these researchers, Pinkett and Lee actually gave the theoretically how we can actually analyze these reinforced foundations. Okay, and due to using this, like, what we do, we actually use a trial and error technique to fix the depth, the spacing, number of reinforcement, the length of spacing, all these we use. So they were actually the first ones to give a theoretical method, okay, analytical method using which we can design the reinforcement to increase the bearing capacity of a foundation. All right. So yeah, so as we already discussed, In the first, so there are three modes of failure, right? So there are three modes of failure. So in the first mode, okay, the shallow foundation on thin layer of soil with dense reinforcement, right? Resting on a rigid boundary. So same, this failure mode is same as what we studied for the geocell under embankment, as I said. Then second is where we have pull out failure, where the number of ties are lesser and or the number of ties are shorter. In that case, we have pull out failure. All right. And the third mode of failure is the tensile failure, right? The tensile breaking failure. Here, the number of ties are long ties, and there are several number of ties given. In that case, what happens? If the design is not correct, the failure will be in terms of breakage. Okay, there will be tensile breakage. So as load increases in that case, the failure propagates from upper layers to lower layers with rupture occurring, and thus progressively the failure continues. So we will see so how where this uh, rupture actually occurs. We will see that in the upcoming slides. Okay, where does this reinforcement actually break? We will see that. So here we can see that for first mode of failure, okay, the first mode of failure, the bearing capacity for the soils with different phi can actually be obtained from this graph. Okay, so for say the soil of 30 degrees and we have UIB ratio zero point 0.5, then if we are considering that the first mode of failure will happen from here we can actually get the this q by q naught ratio. Okay, it is the bearing capacity ratio. Bearing capacity ratio is nothing but the ratio of the improved pressure to the non unimproved pressure, unreinforced pressure, right? So do and also one more thing, we during any design we our target must be to ensure that the bearing capacity ratio is q by q naught ratio is generally uh, around 3 to 4. Okay, so this justifies the cost economies that is involved in this providing of reinforcement and everything. So here we have defined that BCR equal to Q by Q naught. So Q is nothing but the footing pressure on reinforced foundation, and Q naught is nothing but the footing pressure on unreinforced foundation, both measured at the same settlement. Alright. So same settlement means say this is the settlement, this is the pressure. So for unreinforced say it's like this, and for reinforced say it's something like this. So the same settlement, what are the pressures? Okay, so say this is Q naught and this will be Q. This is unreinforced, this is. Now let us see for the other two modes of failure how actually Piccadilly actually derived this derived analyzed how to solve this problem. Okay, analyze theoretically. So here we can see the surfaces AC dash AC A dash C dash and AC actually this A dash C dash and AC actually represent the surfaces where the shear stresses are maximum. Say we consider a level A. Level M is just a level, okay, just a depth, some depth, say Z1, and this is at a depth of Z2 level. So at some depth, if we see the how the shear stress actually varies, you will see that the shear stresses varies about these dotted lines. So it's minimum at the center line, it increases and then it reduces. Okay, and this point at any depth z, okay, remember this, at any depth z, the point at which the shear stress is maximum is given by this distance x naught. Okay, what is x naught? X naught is the point, okay, x naught is the point, sorry, x naught is the point at any depth, okay, at any level depth. I'm describing this at any level, okay, at any depth z, x naught is the horizontal distance from the center line where the shear stress is actually is maximum. All right, that is actually x naught distance. Okay, this dotted line actually represents where the shear stresses are maximum, the variation of the shear stress. And the solid line that we see here, the solid line actually represents the distribution of the pressure, the load that is coming to the soil. Okay, the distribution of that load. So surfaces A dash, A prime, C prime, and AC represent the locus of the maximum shear stress along this rupture of reinforcement or observed. So what happens, as I said before, so this tie is actually rupture along this line, this locus only, where this this shear stresses are maximum. Along at that points, what happened? At that point, this tie is actually rupture or tie is actually break. Okay. So they looked into Bingadelli looked into the variation of vertical pressure and the shear stresses. So as load increases, the load increases, the soil moves down and laterally up. Okay, the soil moved down. The central portion, so we divided it into two zones, zone one and zone. The zone one actually moves downwards, and this zone two actually moves laterally outwards. Okay, the zone two moves like this, and the zone one actually comes down. Okay, this is how the soil moves when we're increasing the load. But so one more thing, generally what happens whenever we put some load, even if you want to, if you do an experiment, you'll see that, say you're responsibility and you're providing some load and you're measuring the displacement of the footing, settlement of the footing at the two edges, left and right edges. Okay, we are measuring the displacement at the left edge and the right. So we'll see that as the load here, you will be increasing the load, the displacement at the two edges won't be same. So in one side it will be a little bit more, one side will be a little bit lesser. So there is a tendency for of rotation. Okay, the tendency of the footing to rotate, right? So there is a tendency for the footing to rotate, but Pinkerton for simplification, they did not consider this rotation. Alright, so they did not consider this rotation. So they just consider the this downward movement. Okay, so they did not consider this rotation. Alright, so just consider that it will come down the soil at the central zone one will come down, and the other portions they will move laterally outwards. So did not consider the rotation of the formation. But practically, what we can say from experiments is that some rotation actually does occur. Okay. So from Bosenick's theory, we can get the this sigma z. Sigma z is nothing but the variation of the vertical pressure, and this tau xz is nothing but the variation of the what? Variation of the shear stresses. Okay. So this is my sigma z, and this dotted line is nothing but the tau xz. So these were obtained from the Bosenick's theory. All right. Now, using those from the Bosenick's theory, they gave this simplified chart, which makes our task very easy. Right. So from here, what we can get from at any depth ratio, that means at any level, we can get this distance x naught. Okay. What is x naught? I already described that in the previous slide. It is very important term. We will be using that. What is x naught? X naught is the distance from the center line at any level. Okay, x naught is the distance from the center line at any level where the shear stresses are maximum. Okay, where the shear stresses are maximum. This is x naught. And one more term we can see here, L naught. What is L naught? L naught is the distance at any level. L naught is the distance from the center line where the vertical stress reduces to 1% of the applied stresses. Okay, the vertical stress reduces at 1% of the applied stresses. Okay, so this 1% is considered because it is considered the 1% which won't affect this uh, won't affect the straining of the reinforcement in any way. Okay, so up to that, so that distance L naught is actually considered. Okay, L naught is the point lateral distance of a center line where this vertical stress reduces to 1% of this Q. Okay, 1% of Q. Now, in failure modes 2 and 3, this the bearing capacity is dependent on the strength of the reinforcement ties, right? Obviously. So what happens? This bearing capacity is directly dependent on the strength of the reinforcement of the tie. Okay, strength of the reinforcement of the ties. So it is actually taken as the minimum. Okay, minimum of the yield strength of the ties and the pull out resistance of the ties. Okay, the pull out resistance of the ties. Okay, so here you can see TD should be less than equal to the load that is coming. The load that is coming onto each reinforcement tie, that should be less than equal to the yield strength of the tie. Obviously, TD is what? What is TD? TD is the reinforcement force in each layer. That is reinforcement force in one layer. Okay, on one layer, right? TD should be always less than equal to the yield strength of the ties and the pull out resistance of the ties. Okay, so uh, this Fy, this yield strength is divided by a factor of Fsy, that is nothing but the factor of safety against rupture. Okay, that reduces the yield strength by certain amount, certain numerical amount, so that we get more conservative value. Alright, and this pull out resistance is also divided by this Fsf, which is nothing but the factor of safety in pull out failure. So obviously the reinforcement force, the force that is coming in each reinforcement, the force, the load that is coming into each reinforcement there, the load that is coming into each reinforcement there, that should be obviously lesser than the yield strength. That is the strength of the ties. That is the tie should not break, right? It should be lesser than the strength of the ties. If the load coming on this reinforcement is greater than the strength of the tie, what will happen? Obviously, it's going to rupture. Obviously, it's going to break, right? So we need to ensure that the load coming on each reinforcement there should be less than the strength, yield strength of the reinforcement, right? And also to prevent more, this satisfies the third mode of failure, and to prevent the second mode of failure, that is the pull out mode of failure, we need to ensure that the pull out resistance is actually higher than the load that is coming on reinforcement, right? So certain amount of load is coming in this reinforcement. This load should always be less than the pull out resistance that the reinforcement is providing. Okay, else what will happen? Else the reinforcement will get pulled out with the soil. Okay, pulled out with the it will get pulled out with the soil. So we must ensure that this pull out resistance is greater than the load that is coming into the reinforcement, and also the yield strength is greater than the load that is coming into the reinforcement. All right. Now this is the free body diagram actually that was used by Pincatelli to actually determine or this summarize all the forces. So here I can see he has taken any reinforcement layer at a level Z. Okay, at level I, at a depth of Z, he has considered a reinforcement layer, and he has considered a soil mass ADCP around that reinforcement layer. Okay, you just consider the soil mass ADCB here, ADCB around that reinforcement layer. Alright, so FB top is nothing but the pressure that is coming on the top of that layer. FB bottom is the bottom pressure that is acting on that soil. Alright, then we have S. S is the upward soil resistance that is acting. Okay, S is the upward soil resistance that is acting, and TD is the upward reinforcement force that is acting. Now a question might come, right? Now a question might come, how is reinforcement force upward? Because reinforcement you're providing like this, right? So reinforcement force must come laterally only, else how will the reinforcement resist that force? Because these reinforcements are strong in tension, right? These reinforcements are strong in tension. Reinforce these forces obviously must come in the lateral direction. Then how come we are considering this reinforcement force TD in vertical direction? The answer to is that is here. Oh, so what happens? Uh, at the verge of when the loads are actually acting, there is a kink that actually develops here. Okay, at the interface where the shear stress is maximum, at that place there is a kink that develops. Okay, so the this reinforcement is not actually straight. Initially, it should be straight, but what happens due to the load? There is a kink that forms on the reinforcement. Due to that, what we consider that this T is actually acting particular only at that point. Only at this point, we consider that this is acting in the vertical direction. And the dotted line here also represents the variation of our shear stress. Okay, you can see that it's not here at level is at the maximum shear stress. So this kink actually makes this TD vertical. Okay, that's why this is acting in the vertical direction. Alright. Now what we can do now, if we just take the equilibrium of the element in the horizontal in the vertical force equilibrium of this element around this element ADCB, we'll get these equations 4 and 5, right? And they assume that this bottom and uh, this bottom forces, okay, this bottom force. So here you can see there are two terms, one where we are writing Q naught and one we are writing Q. So when we take this vertical force equilibrium, this equation 4 represents the vertical force equilibrium when there is no reinforcement. Okay, that's why we are using the term Q naught here. And this equation 5 represents the vertical force equilibrium equation when we are providing the reinforcement. So here you can see this Q is written in place of Q naught. Also, one more extra term that is coming, that is the reinforcement force that is coming here. All right. Now it can be assumed, it is assumed that this it's just obvious to assume that the vertical force, because this vertical force that is acting here, it is not influenced by this reinforcement, right? This vertical force that acts, this acts at the bottom of the soil wedge ADCB, that is actually same in both in unreinforced and reinforced. So if we then using this thing, this if we equate equation 4 and 5, we can get this equation 7. Okay, so all the terms in this equation can actually be directly be obtained by integrating the forces. Okay, by integrating the forces, integrating the stress equation, we can get these terms. Okay, except, okay, this TD value. Okay, except this TD value, all the others we can get. So what we will do, we will use all the others to get this TD value, all the other terms to obtain this reinforcement force, that is TD. Now you can see here the V top is given by integration of sigma z dx. Obviously, sigma z is the vertical force that is acting. So this sigma z will be nothing but the integration from here x to x naught. Okay, from this is 0, from 0 to x naught, this distance of sigma z, right? That will give us the what? The top force that is acting. Then we have this S. S is nothing but the soil resistance, right? The soil resistance that is coming from the shear stresses that is developing. So the shear force multiplied by the thickness of the wedge, that is delta H, we're getting this S, right? Now, Binkert and Lee actually they gave a simplified equation for us so that we can easily determine everything. So this 8 actually transfers to this equation 10. So this 8 equation after integration they represented as a term JQV. This J is a function of Z by V. Alright, and this J is given by this integral here. Okay, and this S is given by I Q delta H, and this I here is given by this integral here. And this J and I, all those things that I have highlighted in blue, these things are were given by Binkert and Lee graphical form, so that easily at any Z by B depth we can easily get the values of this J and I easily that we can get for any value of Z by B for any Z by B, we can get this J and I from graph, okay, given by Pickett. Okay. Now, if we substitute all these JIs and all these other things, we'll get the final equation for our TD, that is the reinforcement force in each layer is this. Okay, so we will be using this equation 14. Okay, so we will be using this equation 14 to actually determine, okay, so actually determine the reinforcement force in each layer. Okay, at each depth we can determine the reinforcement force, right? Now the yield resistance, okay, the yield resistance is given by Fy, right? This yield resistance is given by Fy is equal to WNR TFI by FSY, where W is the width of a single tie, T is the thickness of the tie, and our number of ties per unit length of the footing. Fy is the yield strength, FSY is the factor of safety on it. Okay, Fy is given by this, and what is LDR? LDR represents the linear density ratio. Okay, the linear density of reinforcement. This is the LDR, linear density of the reinforcement. In linearly lengthwise, okay, lengthwise how this reinforcement is varied. Okay, these are strips, right? These are strips. So how much coverage we are providing this lengthwise per unit length. So that is given by this LDR. So LDR is nothing but width of a single tie. So we are providing the reinforcement like this, right? Reinforcement. So this is like this we are providing. Okay, like this, literally like this. So it will have certain width. So width times this width. This is the width of the strips. This width times this width time, this is the lateral, okay, in this plane, in the out of plane direction, okay, like this plane here, like this, you are putting the reinforcement. This reinforcement have certain width, right? So width times the number of reinforcement, okay, number of reinforcement per unit length. NR is the number of reinforcement per unit length. This is lengthwise out of plane direction how many reinforcement you are providing, not this, not vertically how many reinforcement you have. This is lengthwise, per unit length how many reinforcement you are providing. So that W times NR will actually give us the linear density of the reinforcement. So obviously, as highlighted here, the tie force CD needs to be compared to the yield strength Fy to assess the tie field. Okay. Next, so here we determine this TD force, right? The tie force. Okay. So determine this tie force, the maximum force that is coming into the reinforcement. Now next, our next task is to determine the pull out resistance. Okay, that is the pull out. How much pull out resistance is each uh, layer giving, providing? Okay, how much pull out resistance is each layer providing, that we need to determine. So that is given by, so how that has been derived is actually given here. So we have this vertical PBEF. So let us see EF. So see, okay, so this is the locus of the maximum shear stress, right? So this EF length will be giving some anchorage, right? Anchor. This will be acting as an anchor. This is the length that will actually be preventing the pull out of the reinforcement. If this length is short, the pull out forces that will develop, that won't be optimum. Okay. What will happen? If this length is short, the load coming into the reinforcement will actually pull the reinforcement out. We like the reinforcement is will come out with the failure soil wedge. Okay, will come out with the failure soil. So this EF length is actually what? Actually the soil that is providing the anchorage of the reinforcement. It's acting as an anchor of the reinforcement in the soil. So if you can recall, in the for this case, in the for wall reinforced earth wall cases, so here we had a wedge, then we had reinforcement. So this length actually provided of this anchorage into the soil, right? This held the reinforcement in place. If this length is shorter, what will happen? Plot failure will occur. This whole failure, the soil will fall down with the reinforcement. So this reinforcement that is providing here, the length of the reinforcement here is very important. Okay. So the vertical force that is coming in that EF is given by LDR times sigma z dx. Okay. Obviously sigma nothing else. Linear density ratio times the integration of our sigma z. What is sigma z? The vertical pressure that is coming, integrated from 0 to L naught. X naught to L naught, sorry, X naught to L naught. So say this up to here it is X naught, and here it should be L naught. So X naught from here to here we are integrating. Okay, from here to here we are integrating. So L naught, as you all know, what is L naught? L naught is the distance from the center line where sigma b reduces to 1% of the applied pressure. So why 1%? So we consider that this 1% is the limit. Lesser than that, lesser than 1%, this pressure won't have any effect on the reinforcement. Okay, won't be having any impact on the reinforcement. So we consider this L naught length, the up to this 1% pressure, okay, 0.01 times of Q. All right. Now this integral can be represented in terms of this function m, and this function m is given by this equation 19. So Binkatelli, to make our task easier, he represented this function m graphically, so that for any z by b we can easily get the value of m from the chart. Okay. Okay, so uh, finally we have, so vertical EF. So finally this final total. Okay, so the total pull out for total force that is coming is nothing but this VEF times times this is nothing but the overburden pressure. Okay, if we see gamma times Z by B, Z plus B, this thing will is nothing but the expression what I think, uh, sorry, not over burden. This is actually coming from by integrating. Okay, by integrating the total this equation, it is this equation we are getting. And now if we combine this equation 18, this equation and this equation and this equation, finally we can get this equation 22, which is the important equation for the pull out force that is acting. Okay, this is the pull out force that is acting. This B, I think this is not B, this should be, I think, Z plus D. Okay, that is the overburden. That's why uh, because gamma times this term actually comes from the overburden pressure. So this should be actually, I think, Z plus D. D is nothing but the depth of the foundation. Okay, so while solving the problem, I guess uh, this was Z plus D only. There, so I will just check once. Huh? So please check this term once. I will just check once what they are done in the solution of the problem. There they have written Z plus D. So D should be actually depth of the foundation. I think so. There, see here it's written Z plus D. Okay, anyways, so this is the final equation. Okay. Okay, just confirm this once. Okay, what is this D? As far as I know, this I think this Z should be nothing but this D should be nothing but this D should be nothing but the depth of the foundation. Okay, just confirm this once because yeah, I think this should be Z plus D. I will just give me a second. I will just uh, check that if I can get this paper. Because B here they have used as width, right? And D should be the depth of the footing. Just a second. Huh? I'll just see if I can get. Okay, anyways, whatever bit. So I think that should D is nothing but this depth of footing. Okay, as far as I think. Just confirm this once from professor. Okay, by writing a mail to him, or you can just write in the this course page. This what to say? This discussion forum. All right. Okay. What is the question that has been uh, what is the question that has been given in the assignment? Is it for the width one, depth one? Just check once. Over here they provided strip footing of 2 meter. Okay, okay, whatever be it. Just check yourselves once. Okay, I think that D should be depth because see gamma you are multiplying with so say there is any one footing is there. Okay, there is some depth D and a reinforcement here at some level Z from. So Z plus D times gamma. It is the word burden pressure, right? So that's why this term has come. Not V, it should be D. So that D should be actually depth. Okay. So yeah. So as I said, I, J, and M, all these are given in terms of this graphical form for so that we can easily solve. We can easily get this I, M, and J values. These are given by Dinget and Lee in graphical forms. So now let us come to the problem. So this is the same problem that has been given in the class. So we will be solving this step by step, one by one, slowly. We'll see how we will do all the calculations by hand, slowly, slowly. Okay, so that it's easier to understand, right? So that's why I thought that it's better to solve the problem again. So that step by step we can solve it together. So the question is what? Design a strip footing to carry a line load of 1700 kN per meter. The design for the data for the design is as follows. Soil parameters are C is equal to 0, phi is equal to 35, gamma is equal to 17. S is nothing but the Young's modulus of the soil. Mu as the Poisson's ratio of the soil. Then we have the reinforcement parameters Fy, that is the distance to the power 5. Yield strength of the soil of the reinforcement. Then we have the friction and for the reinforcement 28 degrees. We have FSY, FSF. This is the minimum FSF that we should have 2.5 at each layer. Width of ties we have, LDR we have. So depth of foundation is given as 1 meter, permissible 7.25 mm, design life is 50 years. Okay, so what we need to do, we need to determine this, right? We need to determine we need to design this. So what we do as a first step, we choose the width. So let us assume the width of the footing to be 1 meter first. Okay, then you will see if we increase this to 2 meters, how does things change. Okay, we'll see how does things change when we increase this to 2 meters. So first let us do the same thing for 1 meter only. However, it was discussed in the class. And let us assume that the depth of first layer is 0.5 meters. Okay, that is within the discussed range, within the range, right? What was desired range. We need to assume some values, right? So let us assume u. Then vertical spacing, this also you can take as 0.5 meter, right? Number of reinforcement, and let us assume it as 5. Okay, so u, what is the u by b here? U by v is 0.5 by 1 equal to 0.5. It is less than 2 by 3. So mode that's why we are getting mode of failure 2 or 3. Okay, that's why we are designing it that way. Alright, so there are chances of mode of failure 2 or 3. Alright, so now LDR is given. So width time NR is LDR. So from here we can get the number of ties that we need to provide per meter length, that we can get 0.65 and 0.075 is 8.67 ties per meter length of the footing. Alright, now for 35 degree, let me just go to the next slide because there I have that. Now see the solution which was done in the class. Okay, in the solution that it was done in the class, I saw that for 35 degrees they took these values. These values were given. Third, and these values of NQ and N gamma were given. 33.3 and 48. These values were given. Okay, but these values are actually taken from this IS 6403. And IS 6403, if you are following, then the equation. So ultimately, what equation? It was this Terzagh's equation was used, right, to determine the determine this failure, this ultimate bearing pressure, ultimate bearing capacity. This Terzagh's equation was used, but these bearing capacity factors that were given in the that were used in the class, those were actually belonging to basics. Okay, so for that, if you want to use this, I think it's better to use the net ultimate equation of this equation for the net ultimate bearing capacity from IS code. But if you are using this 35 degree and you are using this Terzaghi's equation, then I think it's better. I think it's appropriate to use Terzaghi bearing capacity factors. So there might be some confusion in that. So nothing to worry in the examination, or there is no need to worry. Obviously, you will be provided with this NQ and N gamma values in the question itself. Okay, there is nothing to worry. You will be provided this NQ and gamma question. So nevertheless, I thought that it's important to just tell you this, that I think in the solution that was given, they took the wrong bearing capacities, wrong bearing capacity factors. So let us take this Terzaghi bearing capacity factors only. For examination, no need to worry. This NQ and gamma will be given in the question, so directly you can make use of that. So just so there is nothing, there is no question of confusion or nothing to worry. So directly use the NQ and N gamma values that are given in the question. Okay. nothing to it. So for 35 degree, 41.4 n gamma is increase 41.4 and n gamma is 42. Okay, so now let us put this value 17 into 1 into 41.4 minus 1 plus half 17 into 1 into, so how much does it come? 17 into 40.4 plus half into 17 into 1047.2. 1047.2. So if we divide this by 3, we will get the same bearing capacity. Let's say 349.0, 349 you can take it. 349 kilonewton per meter square. Okay, and for that, for the settlement criteria, I will just do it here. So settlement immediate, this is immediate settlement, right? Remember, this is immediate settlement. B is 1 minus mu square divided by, yes. So allowable settlement is 25 mm. QNP I need to get is 1 minus what is mu, 0.35 square into 2. Influence factor for strip footing flexible, you can take 2, and ES is 30,000. Just check the values once. From here Q and P I will get 427.35 kilometer per meter square. So the minimum of 427.35, and this you need to take. So what is our Q naught? So our Q naught is 349. Okay, this is our Q naught. Okay. Right. So now what will be this Q? What is Q? Q is 1700, that is the load that we should carry, divided by the width. Width we are assuming 1, so divide by 1. So 1700 Newton per meter square. Now we need to calculate this TD force. So for that we will take the help of Excel. Okay, I will just stop this screen and I will just share the other screen. Just a second. We'll just share the screen for you. Just a minute. Okay, so I hope this is visible to you. Alright, so I hope this is visible. So, okay, so let us see. So the first term, so you can see here, this is the uh, yeah. So this is the term for our TD, right? So we need the terms J into B, I into H, Q naught by H. So all these terms, what we will do, we will calculate one by one separately. So, all right. So what is Q naught? What is Q naught? Q naught is how much? We just calculated. What is Q naught? 349. Okay. So you come here, 349 divided by 5, reinforcement times Q by Q naught. What is Q? 1700 by 349 minus 1. Okay, so this much we are getting. So this is same for everyone. Okay, now we have for Z. Okay, so what is the Z? So we are providing at 0.5 meter depth, right? So we are providing at 0.5 meter depth. So what we can do, so Z will be zero point 0.5. First one U is 0.5 and delta H is also 0.5. So all will be sum of 0.5. So up to 2.5. Now what is Z by B? Z divided by B. So what is B that we have assumed? 1. Z by B we got. Now our task is to get the value of this J and this I for each of this Z by B. From where? From this graph. So for Z by B 0.5, for 1, 1.5, 2, 2.5, we can get from this graph. Okay. So for 0.5, what is J? We can take approximately 0.35. Okay, approximately 0.35. Like this, all the values we actually need to take. So that I will cite the values 0.35, 0.34, then again 0.34, 0.33, 0.32. Then we have J into B. So J times B, B what is B? 1, right? Then we have I. So I's again we need to find out. So what are the I's? So I have just done the thing here. One second, just copy that. So I you can see from here. Just enlarge it. So for Z by B 0.5, you can see I is approximately 0.25 here. Then for 1, we have I approximately here 0.18, approximately 0.18. For 1.5, we can take I approximately here 0.13. For 2, we can take I here zero point 0.1, and for 2.5, we can take 0.808 approximately. Alright, so like this, you get I. Then we have I into H. I times H. So what is H? 0.5. Done. Now J times B minus I. JB minus I. We got this. Finally, what we do, we put in this expression. So equal to for 1, right? So you're getting for 1 reinforcement, so 1 by 1 times JB minus IH, it is this, times this Q thing, right? So we got this way. So you just drag it down, we'll get for all the layers. Done. So like this, what we did, we determined the force, okay, the force that is coming on each layer. Okay, the force that is coming on each layer. Now the next thing we need to do is to determine this pull out forces. Okay, this pull out force that is coming. Okay, so let us find that out. So for that, see all the terms. So one by one again we will record all these terms. The first term is twice F LDR. So what is F? F is nothing but actually 10 times 10 of phi u is actually equal to 10 of mu u is equal to mu. So I have written it here. So I will just copy this table. What I can do, I will just copy this table and paste it here. Okay. Now you can see here this F is nothing but 10 of phi u is equal phi mu is equal to mu. So what is phi mu? Phi mu is given as 28 degrees. So 10 28 degrees will be nothing but mu. Alright. So 10 28 degrees will be mu. So let us get this, do this is equal to 2 times 10 of 10 20. 10 of 10 of 28 degrees is 0.53. 0.5317, 0.5317 times LDR. LDR is what? 0.65%, so 0.65. So we get 0.69. Alright, we got the first term, twice F LDR, this we got. Alright, and next is Z. Z is again same, 0.5, 1, 1.5, like that. 2.5, right? Then we have Z by B, that is this by Z by B. Now again for Z by B's, for this different Z by B's, we need to get this M value from here. Okay, this M from here. So for Z by B point 5, we have M as approximately 0.125. Okay, for a 0.5 we can approximately give it 0.125. So let us write this down. 5. Then for Z by B1 it is approximately how much? M is approximately 0.14. Then for 1.5 that is here approximately 0.15. For then for 2 it is here 0.16 maybe, or again so 0.5 only, almost constant here, right? So take 0.15 only. Then for this we can take again 0.15. Okay, so for 2 also 0.15, 2.5 approximately less than 0.15, so you can take 0.15. Not much. Fine. Next is Q by Q. So Q by Q into Q by Q naught. So Q naught will cancel. It's nothing but ultimately Q only. So what is Q? 1700. Now we multiply this M times B. What is B? 1 times this. Right, so we got this first term. Then what is L naught by B? This L naught by B, how can we get? If you recall, for that we need to use this graph. So for various Z by B, we can get L naught by B and S naught by B. So for 0.5 Z by V 0.5, we have L naught by B as approximately 1.5, like that we need to get. L naught by V is 1.55, then again then 2.6, 3.4, 3.5, 4.2. Okay, and X naught by B from here for 0.5 it's approximately 0.55, like that. Okay. 0.5, 0.8, 1.1, 1.4, and 1.65. So you got this. Then what is L naught? L naught by B times B give us L naught. This the same we can carry for X naught. Okay, so L naught minus X naught you can get. Then comes Z plus D. So as per my understanding, this should be Z means this. Z plus D means D is depth, right? Should be 1. Okay. Now comes gamma. Gamma is what? Gamma is 17 times L minus X times L plus Z plus D. So we got this. Alright. So finally what is FF? If we put all the terms here, we can get equal to this term multiplied by this term plus this term, right? From this equation we get this. Now what is that? What are the TD values? These are the TD values. That means copy this here, 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 here. TD. So what is this factor of safety? So obviously what? So what was the target? Our target was that the force on the reinforcement should always be lesser than the pull out resistance, right? The pull out resistance, right? The pull out resistance should be higher, always higher than the force or the load that is coming on each reinforcement, right? The pull out resistance, this pull out resistance should always be higher than this force that is coming on each reinforcement. So if I divide this by tips, we get the factor of safety. You can see the desired factor of safety that was given in the question, that minimum this much factor of safety should be there. It was 2.5. You can see that using this we are getting a factor of safety that is actually higher than 2.5 in all the layers. So in all the layers we have ensured that the factor of safety are actually greater than 2.5. Done, right? Now next is the thickness. How much thickness of the tie thickness means these are thin like this. These are thin plate-like structures, right? So these are thicknesses. So how much the thickness of this tie should be? So our thickness, we have to use this equation here. So Fsy is given in the question as 2.5. I guess so. Let me check once. What is Fsy? Oh, Fsy is 3 actually. Fsy is 3 times Tn. So what is Tn? Tn is this reinforced this load, this yield capacity of the reinforcement. 2.5 into 20.5. So 2.5 into 5 divided by LDR 0.65 times Fy. So what is Fy? Uh, sorry, I just did a mistake. I think. Sorry, this Tn is this reinforcement load that is coming. Okay, this reinforcement load that is coming. Okay, This Tn is the reinforcement load, and this Fy is that uh, this right 2.5. Hmm? So this, let me do it times 1000. I will get in terms of mm. So this times 1000, I'm trying to get the answer in terms of mm. So you can get like this. Understood? So FSY is 3 given in the question. Tn is the load of each load in each reinforcement is nothing but TD here is the same as T here, Tn, T of n at each here, divided by LDR. LDR is given as 0.65 times the yield strength of this type times 1000 to get in mm. So we get this one. So as per the direction, as per the corrosion loss on each phase for 50 years service life 1.35 on each phase, as the above thickness value should be increased by 2.7. Okay, understood? So about 50-year design period on each phase. So there are two phases, right? Two faces, like a two faces of a coin. There are two faces of a steel strip, right? So each face, the thickness must be increased by 1.35 mm. So the total all these thicknesses might be actually increased by 2.7 mm. So this might be increased by 2.7 mm. Okay, how 2.7 mm? Let me write that down. 2 into 1.5. Okay, so these are the thicknesses that you should give it. All right. Now, what is the minimum length? Minimum length of each reinforcement twice L naught. Twice L naught. So L naught is what? L naught is the distance from the center line, right? So twice L naught will make the total length. So total length of reinforcement is nothing but should be equal to twice L naught. Okay, so 2 times this L naught will give us this. So this finally completes our design. Okay, I will just copy this. And go here and paste. Okay, done. So uh, now if say this reinforcement were not provided, then how much width of footing you had to provide? So 1700 divided by what is the bearing same bearing capacity pressure that we got, 349. So almost 5 meter width you had to provide. But now with the use of reinforcement and with the reinforcement, you are able to reduce the width of your strip footing to just 1 meter. All right, with the use of reinforcement from 5 meters, you are able to reduce the width of your footing to just 1 meter. Okay, so this completes this problem. Now if say, if I will just share the screen again. Okay, now if say we have this if we decide to provide the width of the foundation as 2 meters, all the other things remaining same. Okay, all the other things remaining same, all the say this gaps, all the spacing and everything, all the other things remaining same. If we decide to give, okay, if we decide that we want to provide 2 meter with reinforcement, in that case, that is, so actually what we need to do, actually you need to do some trial and error. Okay, actually you need to do some trial and error, and then by doing trial and error, this you need to actually get your optimum width optimum number of reinforcement, all these things you need to get by trial and error. Optimum uh, this spacings also, we just assumed a spacing of 0.5 meter right here in our case. So everything is up to you. So you need to use trial and error to optimize your design. So optimum, you can reduce the spacing, you can increase the spacing, you can reduce the width of foundation, you can increase the width of foundation. uh, okay, you can do all these things, you can manipulate all these things, you can do many number of trials, and then you can optimize, find out the optimum design that is cost effective. Okay, so you need to optimize the design so that our design is cost effective. All right. So now say if the width is 2 meter, now we are thinking that we will provide a width of 2 meter. Now say if this b is say 2 meters, then how will the things change? Okay, now say the width is 10 meter. Now let us check the u by b ratio first. So what is u by b? U is 0.5, we decided. Other things are same. This is 0.25 less than 2/3 of b, less than 2/3, right? So failure will be in 2 or 3 mode, in the second or third mode. Okay. Now let us find out the ultimate bearing chaos in this case. Is n comma 42.4. So how much will it be? 17 into 40.4 plus uh, how much? How much will it be? Please calculate. Half into 17 into 2 into 42.4. 720 plus 17 into 40.4. It's 1407.6. What is Q? Save is by 3. 469.2. All right, correct. Now from the settlement criteria, let us see. So how much will be Q and P? It's 213.68. So what will be our Q naught now in this case? And what is our Q? Q is 1700 divided by 2. But 850. Okay, because the width they are now width you are considering is S2. All right. Okay, now let us again go back. Now let us again go back. Okay, now what is the Q naught? 213.68, and what is Q? 850. Q naught is 213.68. 5, say 5 only are providing. 850. Uh, okay, now what is Z again? 0.5, so 1, like this it will go. Z by B, Z by 2. Now B is 2. Now let us see this J values again from here, this graph. So Z by B is 0.25. Approximate values we will take, okay? Approximate values. So 0.5, 0.25 here. So approximately 0.35 only. Okay, 0.35. Then all are approximate values. So for 0.5 we are taken here. This point, 4 is 0.35. Same. Then let's see, 1.5. So the 0.75 also same only you can take. Okay. Then for 1, how much? A little bit lesser, so 0.34. So we have taken that only, yeah, 0.34. And for 1.25 also you can take 0.33. I will just, I had done this before, I will just copy that. Okay. J into B, J times now 2. Okay, similarly I approximate I values you can get. I will just copy the I values from here, get done that. I just got that before. Let's check all these values as approximate values I have got. I into H, I into 0.5, JB minus IH, JB minus IH, done. Next TD is 1 by 1 times this times this. Okay, so we got the load coming on each reinforcement. Right, let us come to this next part. That is our pull out forces. So this will be same. This will be same for this also. Z. These are the Z's. Z by B's same. Z by 2 plus B you are taking 2. Now M. Now M again we have to get for all these Z by B's. So say for 0.25 it's approximately how much, 0.11 or something. I will just copy the values from here. Okay, but these are also approximate. I just done that back, yeah, just to check one. So I just done that previously. This is the same values. So I'm just copying that. Okay, so that we don't waste time in this, right? So M we get. Now next, what we can do? We can take again this Q. Okay, Q not by Q. This will be Q only. So 850. What is Q? Q is 850 now in our case. Now let us multiply M times B is 2 times this. Done. Done. Now L naught by B. Again for all Z by B's, new Z by B's, you need to get this L naught by B and X naught by B. So I'll just copy the values from here. These are all approximate values. Just check yourselves once. Okay. What value are getting. So L naught will be what? L naught by B times B 2. Same. Okay. So L naught X naught you got. Now L naught minus X naught. Minus X naught I got. Z plus Z. What is Z? Z plus D is 1. And now let's put again 70 times L minus X times Z plus D. Done. Finally FF is equal to this times, sorry, this plus this term. Done. Done. Right. So these are the pull out resistive forces on each layer. Now TDs, let me just copy the TDs. That is the load coming on each layer. Delete it. Right. So this divided by this. So, oh, what did I write here? It should be FF by TD, right? F by okay. So you can see here that for first layer, our factor of safety is actually not greater than 2.5. Okay, it should have been greater than 2.5, but we are not getting 2.5. So this won't actually work. So what we can do is that maybe we can reduce the number of layers to 4 layers, and then we can increase the. So what we can do, we can uh, we have to do another try on this. Okay, maybe if we want to keep the width as 2 meter, what we can do is that if we want to keep the width as 2 meter, what we can do, we can just reduce the uh, number of layers to 4 layers, increase the spacing between the layers, okay, and provide 4 layers, and then check again that if in all those 4 layers this FSF is satisfying or not. So one more trial actually we need to do here for if you want to use 2 meter as the width, because if you want to if you want to use 5 layers, this is not satisfying, right? So this is not actually satisfying in our case. Okay, this should be actually greater than 2.5. This is actually not coming. Nevertheless, you will just find out this. No need to find out this because this design is not working actually. Just paste this one. Okay, this page this for your reference. I will make this. Ah, sorry. So here, so Neville Marquez, right? Okay. Why did it come? So what I will do to draw this. Okay, done. So as you can see here, for the first layer, actually here, the spectral safety is not coming greater than 2.5. All right. So what we can do, we can tweak the design and more a little bit. Okay. So what we can do, so initially, mm, so say UV keep fixed as zero point 0.5 only. H, let we can increase a bit. Okay, or U also you can increase a bit. Say uh, say 0.75, 0.75 or like that, something like that. Okay. Shall we try once? Shall we check once what will happen if we increase this Z a bit? So say we want to provide 4 layers. Okay. Say we want to provide 4 layers. Z, let Z be 0.75 now. Spacing we are increasing a bit. Okay. This fifth layer is not present. So again, this J's we need to calculate. So say zero point 0.4, almost zero point 0.5 only. So it will be approximately 0.35. Then the 0.75. 0.75 means here. Uh, 0.75 also 0.35. Yeah, it's fine. 125. A little bit less. You could take 25. It's fine. Okay, J won't change that much. Then I's. What will be I's? So I's we can take so point for 0.375. It means here approximately here yeah. This is zero point 0.5. This is 0.25. Here, how much should we take? Huh? How much should we take? Say 0.28. Approximately, I'm taking. You just do it a little bit more carefully. 0.75. Say point how much? 0.75 into 0.23. For 1.125 means here. Uh, Say 0.16 or something. 1.5 we are taking 0.18 I know set by b like 1.5 we are taking 0.13. Is much for 0.1.125 is here. How much to take? 0.16. So just do it properly once. Okay. I into H. What is H now? H is 0.75. So this is the TT value. This Z I have to change. This does not exist. So M's you need to do now. M. So M for 1.5 and 0.75. So 0.75 M. What was the M that we took? 0.13. 0.13. 1.5. What must it take? 1.5 and we took 0.15. Okay, so for 1.125 approximately it will be same only. Here. So just take some okay, do it like take the values properly from the graph into. I am just taking some graph estimates and doing it. So 0.1, 0.13. Okay, again this L naught by B naught also you need to do again. So all this 1.5, 7 we can get. That's for 0.375. This is zero point 0.5. This is 0.4. So zero point 0.5, approximately zero point 0.5, and say 1.1. 0.1, uh, 1.5. So how much? 0.75. 0.75. 0.8, 0.8 to 0.8. So this is 0.8. Approximately just I'm taking. Huh? Okay. So L naught I got. Other Z plus Z. Z changed, right? Z changed. This will change. Z. Okay. Still you can see that it's coming 2.3 only. Okay. It's coming actually less than 2.5. Okay, but there might be some mistake also because I have not checked this one. So check the values once again. So I will just write again. So this is also not working. So like this, we need to do some trial and error. Then actually we need to decide. Five is equal to 5 and is equal to n. Okay, you just copy this and put for your reference. Just check. Okay, this there might be some mistake in this because I have not done properly. Just check the values and do once. Okay, so like this by trial and error actually we need to do and we need to find out the this optimum configuration and everything. Okay, there is no other way like this by trial and error. Okay, done. Okay, done. Right. So fine. So with this, we will end today's session. So just practice these some problems a little bit. These are pretty simple, and everything, all data and everything will be provided in the exam only. And next class we will solve some problems regarding this other uses of geotextile and all geosynthetics. That is filtration, separation, all these things. Those problems we will solve. All right. Okay, and whatever we have solved today, just solve these things once more by yourselves. And today I just did live those things I did live, right? So patiently you just see all the values from the chart and take all the values. Now today I just did it rapidly so that we don't waste time. Right? So while you practice, you take the values, all the values properly. Don't refer to these values from the chart that I have taken. Don't refer to the values of J and I that I have taken. You do by yourself, take all the values minutely by yourself. Alright, by minutely you take all the values by yourself and then you uh, do it. Okay, so with this we will end today's session and thank you so much for attending and have a very good evening and a very happy Ganesh Chaturthi to everyone. Okay, thank you, and we will end today's session now.
Thank
Thank you.
you.